Alright guys, welcome back to Underground Science, and in this video we'll be going over another example of acid catalyzed hydration, and we'll be doing the mechanism of it also. Alright, so let's go and get started. So if we see here, right, let's dive into the mechanism right away. Like we've been doing in the previous videos, right, so we identified the nucleophile and electrophile first, so we should be a little quicker at this since we've been doing this for a while now. So this is the nucleophile because it's electron rich, and this is a positively charged, so we know it's electron poor, so that's the electrophile. So let's go and draw all the bonds out in our mechanism. So we're going to have something like this for our reactants, and then we're going to have our hydronium ion, the oxygen bound to 3 hydrogens with our lone pair and a positive charge. This nucleophile will attack, donate its electrons to form a bond with the hydrogen, while these electrons will go on the oxygen. So next we're going to have something like this. Right, and then we're going to have water here because the hydronium ion lost a hydrogen. So we're going to have water, and now we're going to have a carbocation here. Again, just like we did in our previous video, right, let's fix this. It looks like it's a wedge bond. Just draw a normal 2D bond. Okay, so what we did in our previous videos, we said when you get a carbocation like this, you should always look at the carbon right next to it on both sides. So the carbon right next to it is a primary carbon, while this carbon here is not a tertiary like last video, it's a quaternary carbon. Why is it a quaternary carbon? Because this carbon is bound to 4 other carbons. Okay, so but then what level of carbon is the carbon that has the cation on it, right? So the carbocation. This is a secondary carbon, right? Secondary carbon. But if you have a cation on a secondary carbon, you're a secondary carbocation. So wouldn't it be cool if I could take this carbocation and move it here so that we can have a higher level carbon that has the carbocation? So what I mean by that is, right, to make that more clear, let's draw that over here. So what if I were to shift this methyl group onto this carbon? What would happen? So if that were to happen, then we would have something like this, in which now we would have a methyl group here, right? And we would have only one methyl group here. But because we shifted a methyl group here, the carbocation is now on this carbon as compared to this one. And so now if we look at the level of carbons, the carbocation used to be what? Secondary, right? But now the carbocation is not secondary, it's tertiary, because this carbon is bound to 1, 2, 3 carbons. So instead of being a secondary carbocation, now this carbocation is tertiary. So who's better, a tertiary carbocation or a secondary carbocation? Of course, a tertiary carbocation is better, and so that's why we're going to focus on this intermediate next in terms of our reaction mechanism. So once we have this, again, a positive charge indicates, okay, I'm electron poor, and this is going to be an electrophile. So what's going to be our nucleophile? And the answer for that is a water molecule. So this water molecule here will come around and attack this carbon, making our next part of this reaction, our next compound intermediate, which is going to look something like this, in which we're going to have the water molecule, and the water molecule is going to have a positive charge. And now we're just going to get rid of this positive charge by taking another water molecule, since we have so many of it, since it's part of our solution, right? Part of our reagent was water plus sulfuric acid, which is what made this hydronium compound. So part of our reagent is a bunch of water molecules. So another water molecule is going to come in, right? So let's say we have a water molecule here, like that. This water molecule is going to come in and attack that hydrogen, and this bond's going to break and go on the oxygen, and that's going to lead to our product, which let's draw over here. Our product is going to look something like this. Like that. Okay, so this is going to be our product of this acid catalyzed hydration reaction, right? And what we have to focus on here is that first, this oxygen, right, the lone pair of this oxygen attacked the hydrogen, And that means that this will turn into hydronium, right? So this will turn into the hydronium ion. So what does that mean? That the hydronium ion gets made again. Okay, so that means that the catalyst does not get used up. Okay, because what was the catalyst? It's the hydronium ion. That's why it's called acid catalyzed hydration, because this is an acid. Hydronium's acidic. So the catalyst gets made again, so that means the catalyst does not get used up in the reaction. So that's an important part. That's actually an important overall trait of catalysts, right? That they do not get used up in a reaction. They also lower the activation energy of a reaction, but we'll go over that in our Gen Chem videos when we talk about enzymes and in biochem too, when we talk about enzymes and activation energy, thermodynamics for physics. But what we should know first is that we made our catalysts again, so that catalyst does not get used up in the reaction, right? And a last thing to know before we end this video is that, you know how we shifted this methyl from this carbon to the next door carbon? Since we shifted it to the next door carbon, this process is called a 1,2 methyl shift, since we shifted a methyl group to the next door carbon. All right, and that's basically it for this video. And in the next video, we'll continue talking about different types of hydration and more reactions. So I hope to see you guys there.